Suppose we want to train an online continual learning method on this stream of data. What most existing work assume is that the stream is as fast as the training method. However, let's consider a realistic scenario where the stream could be faster than the training method. In this case, we assume that it is twice as fast as the training method. In such case, the method would end up training on half of the stream, eventually skipping every other batch of data. We apply this concept on different algorithms from the online continual learning literature, and we show that AR, the simplest method, end up outperforming all considered methods. Hi everyone, my name is Yasser Ghanem, and on behalf of my collaborators, I will present to you real-time evaluation in online continual learning, a new hope. Online continual learning is a paradigm about training a model through a single pass over a stream of time-varying distribution. Why is OCL important? Suppose we want to predict misinformation on Twitter's data. We know that the stream of Twitter tend to have varying distributions over time due to different trends and emerging topics. And these changes in the data, they could happen in the scale of years, months, or even seconds. So we really need the ability to continually learn over time. Another aspect is that real-time streams are typically very fast. Based on statistics, we know that on Twitter, there are roughly 350,000 tweets per minute. But what if our online continual learning method is not able to keep up with this amount of data? And let's say in this example that it can only train on 335,000 tweets per minute, meaning that the method is 10 times slower than the stream. In such a case, we will end up with a scenario where for training on 1 minute, it takes us 10 minutes, meaning that there is an accumulation of 3.1 million tweets in the remaining 9 minutes. So to make a prediction on these incoming data, we end up using an old model, which is not very ideal. So essentially, efficient learning is key in real-time OCL applications. Now, for current OCL evaluation, they typically allow unlimited training, computational budget, and often they unfairly compares methods with different training complexities. So how can we evaluate OCL in a fair manner? We need a real-time evaluation protocol for OCL that factors in training computational complexity. Now, if we look at the conventional setup for OCL, suppose we want to learn f theta that maps from x to y from a stream S that reveals data sequentially over steps t from 1 to infinity, where at every step, the stream reveals a batch of data that is drawn from a varying distribution. And we represent it here in this green box. Now we need to make predictions on this incoming data. And then the stream reveals the ground truth. And then we evaluate the predictions with respect to the ground truth. Finally, we train f theta and update it to f theta t plus 1. And we keep repeating this. So this is the conventional way. And the issue we see here is that we typically assume that the stream will wait for the model to complete training during these steps. So we looked at the different kind of streams. And we identified two types, the fast streams and the slow streams. And accordingly, we defined this notion called stream model relative complexity, where if the complexity is 1, it means that we can train on all the data. If it's higher than 1, then we're going to be subjected to some delay. So to incorporate this in the training setup, then we modify step number 5, where we incorporate the complexity of a particular method. And based on the value of k, we say, okay, we're going to apply the module operator to decide whether on a particular batch, whether we're going to train on that batch or skip that batch during training. But we still use that batch for evaluation. So let's look at this visually. Suppose we have a method with a complexity of 2. Then when we train on that, the first batch, then we're going to be subjected to some delay here, shown here, which means for the second batch, we are going to evaluate using an old model. And then when we finish training from that first batch, we update our parameters. And as we can see that we're always delayed by one batch. Or in other words, we're skipping every other batch. So to run our experiments, we use the clock data set where the task is given an image. We want to predict the geolocation. In terms of the metrics, we use average online accuracy, which measures the ability of models to adapt to incoming stream samples. Here we show that for any given batch, we're always evaluating on the next training batch. In terms of the methods, here we show all the methods that we considered, along with their training complexities and the corresponding delay, which is just simply 1 minus the complexity. So then the question is, what happens when OCL methods are evaluated under our delayed real-time evaluation setup? Here we show our main finding in the fast stream, where we evaluated each method according to its delay shown in this table. And we see that ER, the simplest method, is actually outperforming all considered methods. Now, another experiment that we were interested in is what if we increase the complexity of the baseline ER such that it has the same delay as each method. So we perform additional gradient steps for ER so that it matches the delay. And then we see this in the next slide. We call this ER minus minus, which matches the complexity of each corresponding OCL method. And we see that even when we do that, even when all are subject to the same delay, then still ER is better than other methods. A third experiment is what if the stream is as slow as each OCL method? So here we don't have the notion of fast streams. All streams are slow. But we allow ER to do additional gradient steps to match the flops or the computational complexity of each method. Again, we see that it outperforms all in all cases. So in conclusion, all evaluated methods underperform the ER baseline in our realistic setup. OCL research should consider training efficiency in evaluations. Thank you so much.